It's mysterious and wondrous. Welcome to the world of relativity. So far, we have introduced spacetime coordinate transformations under special relativity. Before moving on to the laws of motion in this framework, we need a deeper understanding of Lorentz transformations, including concepts like four vectors and invariants. In previous videos, we discussed Lorentz transformations in two-dimensional spacetime, where Bob's movement relative to Alice was confined to the spatial x-axis. In reality, we live in a three-dimensional space. Alice's spatial coordinates include not only the x-axis, but also the y and z-axes. For ease of demonstration, we have only shown the x and y-axes here, without displaying the z-axis. Bob's motion in Alice's reference frame can be in any direction. When the relative motion between Alice and Bob is no longer limited to the x-axis, transforming an event's coordinates from Alice's reference frame to Bob's is called Generalized Lorentz transformation. The Generalized Lorentz transformation can be viewed as a combination of two types of transformations: spatial rotation transformations and conventional Lorentz transformations. First, a spatial rotation transformation is applied to the spatial coordinates in Alice's reference frame. Through the spatial rotation transformation, we can align Alice's x-axis with the direction of Bob's motion. Now Bob moves only along the x-axis of Alice's reference frame, remaining stationary in the y and z-axes. Using conventional Lorentz transformations, we can then convert the spacetime coordinates to Bob's reference frame. In this new reference frame of Bob, the x-axis still represents the direction of relative motion between Alice and Bob. If the final spatial coordinates of Bob's reference frame are not aligned with this, we can adjust the spatial axes of Bob's reference frame to the desired orientation through another spatial rotation transformation. As seen from the analysis above, through spatial rotation transformations and conventional Lorentz transformations, we can achieve spacetime coordinates transformations between any two inertial reference frames. The generalized Lorentz transformation is simply a combination of these spatial rotation transformations and conventional Lorentz transformation. The coordinates of an event in one inertial reference frame can be transformed to coordinates in another inertial reference frame using a generalized Lorentz transformation. Let's examine which physical quantities remain invariant in this process. Since the generalized Lorentz transformation can be decomposed into spatial rotation transformations and conventional Lorentz transformations, we will analyze these two transformations separately, one by one. First, the spatial rotation transformation. As spatial rotation transformations do not involve time, the time component remains unchanged during this process. Furthermore, a spatial rotation around the origin does not change the spatial distance to the origin, meaning that the sum of the squares of the spatial coordinates remains invariant during the rotation. For example, a rotation around the z-axis changes the x and y coordinate values, but the sum of their squares always remains unchanged. Next, let's move on to the conventional Lorentz transformation. We should be able to use the Lorentz transformation to convert the coordinates of an event from one reference frame to another. But most of us may not have noticed that the coordinates of an event in different reference frames conform to a hyperbolic equation. This relationship can be derived using the Lorentz transformation equations. Apply the Lorentz transformation formulas for t' and x'. Expand the algebraic expressions and perform some simplifications. The difference between the squares of t and x remains invariant before and after the Lorentz transformation. In other words, the difference between the squares of the time coordinate and the spatial coordinates of an event in different inertial reference frames is an invariant. Additionally, since there is no relative motion along the y and z axes between the reference frames, the coordinates along the y-axis and z-axis do not change under the conventional Lorentz transformation. We have listed the invariants under the spatial rotation transformation and the conventional Lorentz transformation. Based on this, we can identify the invariant under the generalized Lorentz transformation. This invariant can be understood as follows. An event has different spacetime coordinates in different reference frames, but the square of the time coordinate minus the sum of the squares of the spatial coordinates for the same event always remains invariant. The invariants in the generalized Lorentz transformation are powerful tools for deepening our understanding of special relativity. In upcoming videos, as we introduce and explore more physical quantities that conform to the generalized Lorentz transformation, invariance will play a crucial role. Up to now, our use of the Lorentz transformation has primarily involved applying it to spacetime points, that is, the coordinates of events. We use the Lorentz transformation to transform coordinates between different inertial reference frames. In fact, Lorentz transformations can act not only on the coordinates of spacetime points, but also on other physical quantities. If a physical quantity consists of one time component and three spatial components, and its component values satisfy the relations of the generalized Lorentz transformation, then this physical quantity is called a four-vector. Let's look at some common four-vectors. The spacetime coordinates of an event, which we have been discussing and demonstrating, satisfy the relations of the generalized Lorentz transformation, thereby qualifying as a four-vector. The displacement vector is also a four-vector. It is defined as the difference in spacetime coordinates between two events. On a spacetime diagram, the displacement vector can be represented by a directed line segment between two events. Through some simple derivation, we can determine that the displacement vector also satisfies the generalized Lorentz transformation relations. So the displacement vector is a four-vector. There are two other important four-vectors, for velocity and for momentum. We will introduce their definitions and properties in future videos. The partial derivatives of a scalar field in spacetime, taken across different dimensions, are referred to as the gradient of the scalar field, which constitutes a four-dimensional vector. Unlike the four vectors mentioned earlier, this is a covariant quantity, rather than a contravariant one. In simple terms, the gradient of a scalar field does not conform to Lorentz transformations, but instead satisfies the inverse of these transformations. While we typically describe quantities that fulfill Lorentz transformations as four vectors, some literature also refers to covariant vectors that satisfy the inverse transformations as four vectors. The concepts of contravariance and covariance are primarily introduced and elaborated upon in general relativity and field theory. The values of a four-vector in different inertial frames of reference satisfy the generalized Lorentz transformation, which includes spatial rotation transformation and conventional Lorentz transformation. From the same derivation as for spacetime coordinates, it is evident that the square of the time component minus the sum of the squares of the spatial components is invariant. The spacetime interval, which we will explain next, is the invariant of the displacement vector. The spacetime interval is an important concept in relativity used to describe the separation of events in spacetime. The spacetime interval is defined by the invariant of the displacement vector. The displacement vector is the difference in coordinates between two events in spacetime, and it is a four-vector. Therefore, the sum of the squares of the spatial components minus the square of the time component is an invariant. This quantity does not change with the reference frame. As long as the two events are fixed, regardless of the inertial reference frame, the sum of the squares of the spatial components minus the square of the time component will be a definite value. This invariant is known as the spacetime interval between the two events. It can be less than 0, greater than 0, or equal to 0, and we will discuss these cases one by one. When this invariant is less than 0, we say the two events are time-like separated. In two-dimensional spacetime, it means that the absolute value of delta t is greater than the absolute value of delta x, indicating that the time interval between the two events is greater than their spatial separation. Time-like separation is a type of separation where the time interval is predominant, and in any reference frame, the time interval between these two events will always be greater than the spatial interval. For events that are time-like separated, the square of the proper time, denoted as delta tau squared, is defined as the difference between the square of the time interval and the square of the spatial interval. The proper time itself is just another way to describe the space-time interval, and for events that are time-like separated, their proper time is a positive real number. In different reference frames, both the time interval and the spatial interval between two events may vary, but the proper time remains invariant. There is always a reference frame in which the spatial interval between two time-like separated events is 0. In this frame, the time interval is minimized compared to other frames and equals the proper time between these two events. A 0 spatial interval indicates that the two events occur at the same location. Therefore, the time elapsed between two such events represents the passage of time for an object that remains stationary. This elapsed time is what we call the proper time, which is the actual time experienced by the object itself. When transformed to other inertial reference frames, if the object is moving in this frame, then measuring the time interval of this moving object will be greater than the proper time it experiences itself. This is also what we previously referred to as the time dilation effect. Let's move on to space-like separation, which occurs when the time interval between two events is less than the space interval. Space-like separation is a type of separation where the spatial interval is predominant, and in any reference frame, the spatial interval between these two events will always be greater than the time interval. Two events that are space-like, separated, cannot have a causal relationship because no process slower than the speed of light can transmit information from one event point to another. Moreover, there is always a reference frame in which two space-like separated events occur simultaneously. When the spacetime interval between two events is 0, it is called light-like separation. Similarly, two events that are light-like separated remain light-like separated in different reference frames. It's important to note that, in the context of relativity, a 0 space-time interval between two events does not necessarily mean that the two events are identical. Rather, it indicates that they are separated by light-like separation. The space-time interval, as an invariant between two events, does not change with the reference frame. This property makes the space-time interval a fundamental tool for describing the structure of spacetime. A clear understanding of the space-time interval is the basis for further exploration of special relativity.